Maglev is a transport method that uses magnetic levitation to move vehicles without touching the ground. With maglev, a vehicle travels along a guideway using magnets to create both lift and propulsion, thereby reducing friction by a great extent and allowing very high speeds. The Shanghai Maglev train, also known as the Transrapid, is the fastest commercial train currently in operation and has a top speed of 430 km per hour. The line was designed to connect Shanghai Pudong International Airport and the outskirts of central Pudong, Shanghai. It covers a distance of 30.5 km in 8 minutes. Maglev trains move more smoothly and more quietly than wheeled mass transit systems. They are relatively unaffected by weather. The power needed for levitation is typically not a large percentage of its overall energy consumption. Most goes to overcome drag. As with other high-speed transport, maglev trains hold the speed record for trains. Vacuum tube train systems might allow maglev trains to attain still higher speeds, though no such vacuum tubes have been built commercially yet. Compared to conventional trains, differences in construction affect the economics of maglev trains, making them much more efficient. For high-speed trains with wheels, wear and tear from friction along with the hammer effect from wheels on rails accelerates equipment wear and prevents high speeds. Conversely, maglev systems have been much more expensive to construct, offsetting lower maintenance costs. Despite decades of research and development, only 2 commercial maglev transport systems are in operation, with 2 others under construction. In April 2004, Shanghai's Transrapid system began commercial operations. In March 2005, Japan began operation of its relatively low-speed HSST Linimo line in time for the 2005 World Expo. In its first 3 months, the Linimo line carried over 10 million passengers. South Korea and the People's Republic of China are both building low-speed maglev routes of their own designs, one in Beijing and the other at Seoul's Incheon Airport. Many maglev projects are controversial, and the technological potential, adoption prospects and economics of maglev systems are often debated. The Shanghai system was labeled a white elephant by rivals. Development. In the late 1940s, the British electrical engineer Eric Laithwaite, a professor at Imperial College London, developed the first full-size working model of the linear induction motor. He became professor of heavy electrical engineering at Imperial College in 1964, where he continued his successful development of the linear motor. Since linear motors do not require physical contact between the vehicle and guideway, they became a common fixture on advanced transportation systems in the 1960s and 70s. Laithwaite joined one such project, the Tract Hovercraft, although the project was cancelled in 1973. The linear motor was naturally suited to use with maglev systems as well. In the early 1970s, Laithwaite discovered a new arrangement of magnets, the magnetic river, that allowed a single linear motor to produce both lift and forward thrust, allowing a maglev system to be built with a single set of magnets. Working at the British Rail Research Division in Derby, along with teams at several civil engineering firms, the transverse flux system was developed into a working system. The first commercial maglev people mover was simply called Maglev, and officially opened in 1984 near Birmingham, England. It operated on an elevated 600-metre section of monorail track between Birmingham International Airport and Birmingham International Railway Station, running at speeds up to 42 km per hour. The system was closed in 1995 due to reliability problems. History. First maglev patent. High-speed transportation patents were granted to various inventors throughout the world. Early United States patents for a linear motor-propelled train were awarded to German inventor Alfred Zedden. The inventor was awarded U.S. Patent 782,312 and U.S. Patent Re 12,700. In 1907, another early electromagnetic transportation system was developed by F. S. Smith. A series of German patents for magnetic levitation trains propelled by linear motors were awarded to Hermann Kemper between 1937 and 1941. An early maglev train was described in U.S. Patent 3,158,765, Magnetic System of Transportation, by G. R. Polgreen. The first use of maglev in a United States patent was in Magnetic Levitation Guidance System, by Canadian Patents and Development Limited. New York, United States, 1913. Émile Bachelet, of Mount Vernon, Y, demonstrated a prototype of a magnetic levitating railway car. New York, United States, 1968. In 1968, while delayed in traffic on the Throgs Neck Bridge, James Powell, a researcher at Brookhaven National Laboratory, thought of using magnetically levitated transportation. Powell and BNL colleague Gordon Danby worked out a maglev concept using static magnets mounted on a moving vehicle to induce electrodynamic lifting and stabilizing forces in specially shaped loops on a guideway. Hamburg, Germany, 1979. Transrapido 5 was the first maglev train with long-stator propulsion licensed for passenger transportation. In 1979, a 908 meters track was opened in Hamburg for the first international transportation exhibition. Interest was sufficient that operations were extended 3 months after the exhibition finished, having carried more than 50,000 passengers. It was reassembled in Kassel in 1980. Birmingham, United Kingdom, 1984–95. The world's first commercial maglev system was a low-speed maglev shuttle that ran between the airport terminal of Birmingham International Airport and the nearby Birmingham International Railway Station between 1984 and 1995. Its track length was 600 meters, and trains flew at an altitude of 15 millimeters, levitated by electromagnets and propelled with linear induction motors. It operated for nearly 11 years, but obsolescence problems with the electronic systems made it progressively unreliable as years passed. One of the original cars is now on display at Railworld in Peterborough, together with the RTV-31 hovertrain vehicle. Another is on display at the National Railway Museum in York. Several favourable conditions existed when the link was built. The British Rail Research Vehicle was 3 tons and extension to the 8-ton vehicle was easy. Electrical power was available. The airport and rail buildings were suitable for terminal platforms. Only one crossing over a public road was required and no steep gradients were involved. Land was owned by the railway or airport. Local industries and councils were supportive. Some government finance was provided, and because of sharing work, the cost per organization was low. After the system closed in 1995, the original guideway lay dormant. It was reused in 2003 when the replacement cable-hauled aerail link cable liner People Mover was opened. Emsland, Germany, 1984–2012. Transrapid, a German maglev company, had a test track in Emsland with a total length of 31.5 kilometers. The single-track line ran between Dorpen and Laden with turning loops at each end. The trains regularly ran at up to 420 kilometers per hour. Paying passengers were carried as part of the testing process. The construction of the test facility began in 1980 and finished in 1984. In 2006, the Laden maglev train accident occurred, killing 23 people, found to have been caused by human error in implementing safety checks. From 2006, no passengers were carried. At the end of 2011, the operation license expired and was not renewed, and in early 2012 demolition permission was given for its facilities, including the track and factory. Japan, 1969. Present Japan operates 2 independently developed maglev trains. One is HSST by Japan Airlines and the other, which is more well known, is SC Maglev by the Central Japan Railway Company. The development of the latter started in 1969. Miyazaki test track regularly hit 517 km per hour by 1979. After an accident that destroyed the train, a new design was selected. In Okazaki, Japan, the SC Maglev took a test ride at the Okazaki exhibition. Tests through the 1980s continued in Miyazaki before transferring to a far larger test track 20 km long, in Yamanashi in 1997. Development of HSST started in 1974, based on technologies introduced from Germany. In Tsukuba, Japan, the HSST-03 became popular in spite of its 300 km per hour at the Tsukuba World Exposition. In Saitama, Japan, the HSST-04-1 was revealed at the Saitama exhibition performed in Kumagaya. Its fastest recorded speed was 300 km per hour. Vancouver, Canada and Hamburg, Germany, 1986–88 In Vancouver, Canada, the HSST-03 by HSST Development Corporation was exhibited at Expo 86 and ran on a 400-meter test track that provided guests with a ride in a single car along a short section of track at the fairgrounds. It was removed after the fair and debut at the R-Expo in 1987, and now on static to display at Okazaki Minami Park. In Hamburg, Germany, the TR-07 was exhibited at the International Traffic Exhibition in 1988. Berlin, Germany, 1989–91 In West Berlin, the M-Bahn was built in the late 1980s. It was a driverless maglev system with a 1.6 km track connecting 3 stations. Testing with passenger traffic started in August 1989, and regular operation started in July 1991. Although the line largely followed a new elevated alignment, it terminated at Gleisdreieck U-Bahn station, where it took over an unused platform for a line that formerly ran to East Berlin. After the fall of the Berlin Wall, plans were set in motion to reconnect this line. Deconstruction of the M-Bahn line began only 2 months after regular service began. It was called the Pundai Project and was completed in February 1992.